Hello, everyone. My name is Roberto Isernia. I'm part of the NI Emerson team here in EMEA, and together I have the honor to present with our team, with my colleague Anna and the WIREFLOW team, this webinar about a product called Lundby, which is a compact and powerful data logger and disturbance recorder made by WIREFLOW using the NI software and hardware tools. We will see during the webinar the capabilities of Lundby and where to use it. We'll see in details all the features of the product, and then we will have a practical demonstration that will go directly on the details live of what Lundby can do. In specific, if we can go to the agenda, there will be a presentation made by Anna, presenting our approach of scalable and open hardware and software platform. And then, as I said, the WIREFLOW team will present Lundby, and then there will be a live demonstration of the product. In the end, there will be a question and answer session. I kindly ask you to write in chat in case you have questions. We will try to answer directly in the chat, and then we will articulate and discuss in details the questions at the end. So for the moment, it's all on my side. I will be back at the end on the Q&A session, and now it's the stage is for Anna.
Thank you, Roberto. So welcome to this webinar. I'm Anna Pedale. I'm a solution marketing manager for the electrical machinery market in NI. And I want to start, as you know, NI is now part of EMERSON. It is a leader in industrial automation, but we are still continuing investing in innovation, in test automation and automated measurements. So still remain our focus because we have a 45 years in track record of this market. And we want to continue investing and give you the system and application that enable you to cover the entire product workflow. So from design and prototyping to the automation validation and then to production. As you know, we cover several industries from aerospace and defense, transportation, semiconductor. My focus is more on the electrical machinery. That means industrial equipment, building automation, HVAC, white goods, power tools. So several industries. But yeah, our focus remain on automated tests and automated measurements. So I want to start with our goal to underline that our main objective is to give you this system application that are flexible, modular, intelligent, so you can really do innovation and embrace engineering challenges that you have today and do innovation for the future. So this is our goal. It's simple, but it's really impactful on what you do every day. And today, with WIREFLOW, we will see an application in data logging and remote monitoring. So I want to start talking to you about the trends in this type of application. So of course, the sustainability and energy efficiency, as you know, we have this, so it's important, and we have this important knowledge on environmental impact. So this is really important every day. And also we need the data logger that are energy efficient. So this is important. Also, as you know, the technology is improving. We have complexity in our products and also advanced sensors. So the data logging is in a type of application that is used in several industries because we need the precise data collection in order to take decision on the data and not on the events. Then industrial Internet of Things, as you know, is another important trend in the manufacturing. We need node, so solutions that are edge computing, so we can be really fast, close to where we are measuring to take decision and not to go to the cloud and come back. So to have real-time insights on your data. And then focus on data security, compliance. As you know, we need that the data are safe. So we need to trust in our data collection. So considering this trend, what are the challenges and the application challenges that you face every day? As we say, the complexity of system. So this means that we need also tests that enable you to test in easy way your equipment, your products, and go to the market really fast. Because we have complexity in the introduction of IoT, of artificial intelligence, predictive maintenance. So we have several aspects and our products are complex. So we need to handle this complexity. And I love saying that we want to help customers to test your product and not test your patients. So this is important for us. Then data integrity and system reliability. So we want that the data that we are connected are reliable. And if we have power loss, connection loss, so we want that our system, our nodes are able to capture data also in this false situation. Of course, if we program it in the right way. Then another challenge is the integration in the infrastructure that you already have in your company, in your laboratory, in your production side or validation side. So we want integration with other software, other protocols, platform, tools, hardware. So an open solution and platform is another important aspect to embrace this challenge. Then limited access to real-time environment. So sometimes we arrive in production without testing our products in real environments with conditions that are that respect the reality. So it's important to simulate real-world condition, simulate faults in order to arrive in production without any surprise that require to come back and lose time and cost. And then visualization and analysis. So it's important to have a real-time dashboard, post-test analysis to check and to see if our product, our system is going in the right way, and have insight in the data that are not raw data, but are data with the metadata, so that you can really see the status of your systems. So, and I, for these kind of challenges, give you the application, hardware and software, and then with the WIREFLOW, we will see the integration they did with our system in the control and embedded test and monitoring application. So let's see what is the NI platform to cover this kind of application. Of course, we have several form factors, from a cost-optimized solution in data acquisition that enable you to have, as I said, cost-optimized systems with a resolution up to 20 bit, with 16 or 32 channels analog input, with a solution in the second bucket more flexible that enable you to have a modular systems with more than 200 modules that you can select for the type of measurements that you want to do, and is compact and rugged. So we have on the top the compact DAC that is desktop based, it's USB and Ethernet, and then the compact trio solution that we will see in details later when we have a real-time operating systems. And then if we want a high density channel solution, so a channel density solution for more performance, we have another solution that is in the third bucket, that is the PXI with up to 28 bits of resolution with improvements in performance. And then the last one, if we need and we have extreme environments, we need an ultra rugged solution. We have the field DAC that enable you to work really in extreme condition. For example, temperature range from minus 40 degrees Celsius to 85, and then it's IP 65 and 67 solution. So it's for ultra rugged system. So now I want to focus more on the compact trio. As I said, we can use this solution for control and remote monitoring because it's a rugged, is an embedded computing platform, and it's used for edge computing. So we will see later in the demonstration from WIREFLOW. We have a real-time operating system that is Linux, and we have also a programmable FPGA inside this system that we can use if we need a really deterministic control loop. We can use, as I said, in these two different situations. For embedded test and monitoring, I mean, for example, structural health monitoring, when you have several measurements like vibration, string gauge, and then you can use also for electrical power monitoring, edge computing, as I said, with the sensor measurements. And compared to other PLC in the market, you have higher speed, precision, synchronization, and signal conditioning that is in all of the more than 200 modules that you can use in this flexible solution. Then it's mobile and portable test systems, and then you can use also if you want to do hardware in the loop, so you want to simulate all the environment where this controller will be, and then test the software in the control unit, or do software in the loop, so modeling the entire software and environment and simulate it. Instead, for the control side, you can use this platform for high-speed automation system, controls application, rapid control prototyping, and as I said, we have an FPGA inside, so you can use for dynamic, deterministic control loop. Again, this is an overview on the hardware. Instead, from the software side, you can use LabVIEW, of course, LabVIEW real-time FPGA and system link. I will be very fast, but if you are curious, you can chat me. I can give you more details. So LabVIEW, as you know, is a graphical programming environment. So in the same thing you are thinking your project, your program, you can realize it in this graphical data flow. And then there is an additional module that is GWeb development software that enables you to create a web-based user interface. Instead, for programming real-time and FPGA that they say are part of the compact trio solution, you can use the module LabVIEW real-time and the LabVIEW FPGA with the several libraries and hardware APIs. So you can use the LabVIEW environment to program your node and solution. And then finally, SystemLink, that is a trust centralized platform that enables you to manage your remote asset and system that you have, checking the system health, monitors of the system, capture data, analyze that, have a sort of a dashboard on the system, and have insight on your data. It's of course connected with all of the other tools that you have, that we have in NI. So I want to conclude with the benefit of this kind of platform, software-centric, and the hardware solution that I show you that enable to have hardware that is really rugged, where you can trust because you can have insight on your data. It's safe, so you have safe data. You can reduce development time because you can have a flexible solution. So it's able to embrace also different condition requirements that you can have in the future. You can do your analysis, control analysis with the really high performances, and you can reduce the wiring overhead with the time-sensitive networking that is in the compact trio, and leverage this open and secure platform. So these are the benefits from this solution that I show you really fast, but if you have questions, please let me know. And now I want to handing over to Stefano from WIREFLOW that will show you their great data logging application and what they did in the market with NI products. Thank you.
Thank you, Anna. Thank you.
Thank you, Anna. So I am Stefan Mattsson from WIREFLOW, and I will do a presentation together with my colleague Jonas Mellroth of the Lundby Data Logger and Disturbance Recorder. I will start to show you how we use the terms data logger and disturbance recorder and what's the difference between these two operation modes are. In the standard data logger mode, the Lundby will do a continuous monitoring and logging of data. And since this is made all the time, the sampling rate will be at a lower rate and data resolution will also be at a lower rate. And then we have this other mode called disturbance recorder or event logger, and that is typically used when we have an abnormal event, a fault or something that we want to look into detail happens. And when this happens, we do a high-speed recording with a high sample rate and a high data resolution. And this is done for a shorter time. And when to start this recording, we need to have a trigger. So a trigger is used to specify at what condition we shall start this recording. And the recording will be done with a pre-triggering recording and a post-triggering recording. This is what you usually have used a digital oscilloscope for. You can use a digital oscilloscope to set up a trigger and you can store data onto a small memory on the oscilloscope for the channels that you have. So we can see the Lundby is really expanding this oscilloscope, this data recording to unlimited almost number of channels. We can have one channel or we can have 100 channels. We can have really large memories, so we can record at high speed for several minutes if we want to do that. So the Lundby is both a standard data logger and a disturbance recorder. The architecture of the Lundby is that it's based on, as Anna mentioned, on NI hardware. So on this picture here, we see that each Lundby logger node is a compact trio. It could also be a PXI. It's a very robust design. It's designed for 24/7 operation. All the nodes that you have are connected with Ethernet cables, could be copper cables or it could be fiber cables. And I use this time-sensitive networking, meaning that all connected nodes are synchronized with a better synchronization than 1 microsecond. And it's a very robust system. So if one of these Ethernet cables are removed or lost for a short time, data will be stored locally on the node. And then when cable is restored, the data will be sent to this central storage. So in the end, all data will be stored on this central storage, but we have local storage on each node that can be used while we're doing high-speed event recording and also when we have some problems with the network. So it has both functionality for local storage, triggering and data collection, these Lundby logger nodes here. So as we mentioned also once again, so we are using the NI hardware, and we can use compact Rio, compact DAC, PXI, and field DAC. The Lundby embedded software is using the DAC, the NI DAC MX software interface. So any NI hardware that is supporting the DAC MX software drivers can be used within the Lundby system. If we take a more closed look into the logger node, we can see that each logger node has this functionality. It has the data collection I/O, and that can be of different types of modules. We have embedded Lundby software that is running on the local CPU. We have a local storage, and we have a synchronization function that makes all these logger nodes to be synchronized in the data collection. So in normal operation, all I/O is sampling at a high rate that is used for this event recording. So data is sampled at high rate coming into the embedded software of the Lundby software, where data is reduced to a lower rate before sent to the central storage. And also these trigger conditions are monitored by the local Lundby software running on the CPU. So when a trigger condition occurs in one of the nodes here, this information is sent to all other nodes. So all nodes know that a trigger condition occurred in the system. And at this point, all nodes will stream data to the local storage at a really high speed. So we have a really high speed data storage for a shorter time, which is the post triggering time. So after the post triggering time has elapsed, we have a lot of data in all the Lundby logger nodes, and then after this recording, all data is sent at a slow speed into the centralized data storage. So we have Lundby system is a data logger for the NI hardware. We have also another software called NI Flex Logger that is also using the NI hardware. I would like to mention how we see on the differences and the different strengths of these two products. We can see in the bottom that they're both using NI hardware. They are both very scalable and can be used for distributed logging with good synchronization. Flex Logger is a very flexible data logger. It's really easy to use HMI, quick setup, and you can have in minutes you can set up a system in your lab to do some recording. It's using a PC for Windows for control and storage. Lundby, on the other hand, is more designed for a 24/7 robust logging application. It's using not Windows, instead it's using the real-time targets for management. The HMI is not as easy to use as Flex Logger. It's more takes some more time to do the setup, but the intention with Lundby is to make the setup once, and then you put the system in 24/7 logging operation for weeks or months or years. Before handing over for Jonas to do in the demonstration, I would like you to know that we have an application note on our website where we describe how Lundby is used in a practical example at Forsmark nuclear power plant in Sweden. So they have several of these Lundby logger nodes that is used on that site. So please visit our website for this case study if you are interested. And with that, I will hand over to my colleague Jonas to do a practical demonstration of the system. So Jonas, please go ahead.
Yes, so my name is Jonas Melroth, and I'm one of the architects and developers of the Lundby data logging system, and I'm going to demonstrate some of the features of the system. And to do that, we're actually going to use the support hardware we use for this case study Stefan mentioned. And this is for Forsmark, and you see that on in the image to the right. You can also see a live feed of the system running on Linus, and you will also see this during the demonstration. So in the top part of this test rig, we have one station or one node, and in the lower part we have another node, and at the very bottom we have a main switch. All of these are connected via Ethernet cables, or in this case it's actually optical Ethernet cables. Each of the nodes consists of a compact Rio, a slave chassis, a CDAC, a switch, and redundant power supplies, and as Stefan mentioned, a local data storage intended to be run 24/7. I also want to mention that you see in the live feed from Linus that we have status lights on top of the test rig. To the left is the status of station 0, and to the right is station 1. And they have a different blink pattern depending on what they're actually doing. So if it's black or off, like the right one, it's not active in any configuration. A slow blinking, like the left one, it means that it's idle and waiting to be active in a trigger occasion. Fast blinking means that it's actively logging data to the local disk. If there's an asymmetric blinking pattern, that indicates a warning, an alarm, and that's designed so that an operator can be on site and see that the system is working or what it's actually doing, even without having a screen connected to the system. And Stefan mentioned that we rely on high time synchronization between the nodes, and a normal setup with this using the 802.1 AS network time synchronization is having one external clock that's fed into the master switch, and the master switch then distributes this clock to the different node switches, and they in turn distribute the clock to the compact Rios. Internally, the compact Rios and CDACs, they're using an internal oscillator, but that one is phase locked to the network time. So everything should be within, as Stefan mentioned, within 1 microsecond, and we will hopefully see that. On the master switch, we also have the Lundby PC running, connected to that one. And we will see the operator interface, which is the GUI. And we also have streamer servers running in the background on the PC. And the streamer service is responsible for fetching data from the local storage once it's available. And this is intended to be run without any operator having to intervene or have to do any action. It runs in the background. And for the demonstration purposes, we also have a sine wave connected to node 1, and we have a digital input connected to node 2, and we will use that for the demonstration. As Stefan mentioned, we rely on DAC-MX. So we have the hardware channel, the hardware layer, and on top of that, we define virtual channels. We don't use MAX to define the DAC-MX channels, but we use the same APIs in the application. And on top of the virtual channels, we also use something we call calculated channels. And calculated channels might be derived channels for frequency measurement, amplitude measurement, RMS measurements, etc. And one of the big benefits that we see is that the triggers can combine virtual and calculated channels at different sample rates. So if you have a calculated channel, for example, RMS just updating once a second, that can still be used together with the virtual channels to create the trigger part. And triggers can also span multiple nodes, so that if a trigger is detected on one node, it will automatically trigger the data logging on other nodes if the same trigger is defined. So what am I going to show you? I'm going to show you how we add a new node to an existing system while it's actually logging. And I'm going to restore that from a backup, and hopefully we will see that it picks up logging together with the other nodes. And this is a typical example where you have a 24/7 system running, and you have one node going down for some reason, and you have to replace it. And doing this, it should be done without affecting the logging capabilities of the other nodes. I will show you how we solve triggered acquisition, and then if we disconnect the node while we're actually logging data, is that affecting the system in any way, or can we just get the network up again and then see that it's working? And I'm also going to demonstrate what happens if we have a trigger detected while a node is disconnected, or while two nodes, they are disconnected and don't see each other. So without more information from that, we jump into the user interface of the Lundby data logging system. So this is, as Stefan said, kind of a rudimentary operating interface. It's intended to be run, and you just need to check it when there is something wrong. For example, if the status lights indicate something. So in this case, we see that we have station 0 running. We see that it's very nicely synchronized to the master clock. It's like tenths of nanoseconds, maybe 20, 30 to 40 nanoseconds time sync offset from the master slave. There's nothing going on in this system at the moment. And to make this, I'm going to start a trigger. I'm just starting logging all the data on this station 0. And we see that we have an active trigger, and we see that we are running data. And next, I'm going to search the system and add a new node. And in this case, there is a node detected. We're using the multicast, the UDP multicast to detect new nodes. This node is not used by anyone, so we can adopt that to this system. I'm going to name this station 1, because that's the name we used. And while this is being added, it's being known to the user interface. So we see that we have a new node in the system. We know the IP address, but we don't know anything about it until it's completely inserted into the system. It will take a while to reboot. And while this one reboots, we go back into the main interface, and we see that a node that is not network connected, that has a yellow background on the node. And you can also see the LEDs, the status lights, they're now blinking differently. So we have an asymmetric blinking pattern on the right, and that means that we have an alarm. And in this case, it's because we don't have any connection to the stream receiver. And in just a minute, we will be back into a slow blink again. And finally, I'm going to restore this one from a backup. So let's restore this. I don't want to do a reboot for the demonstration purposes. So instead, I'm going to jump in and do a software restart. And that's because that's quicker for the demonstration. So you see on the live feed from Linus, you see that the left light is blinking quite fast at the moment. And at the moment, the right one is black, meaning that it's not doing anything. It's not started yet. I can see that in the main user interface that I have a yellow background, meaning that there is no connection at the moment. So I'm expecting this one to be up and running in a minute. And once it's up and running, we should see the blinking pattern coming up. And we see that it's starting, it warns that it's not really ready yet because it has to connect to the stream receiver in the background. And once it's going up, we see that it picks up and start logging data also from this one. So we see that the demo all channels is now reporting that I have 2 nodes participating in this logging session. And I have both of them reports that they have 1 trigger count. And you can see on the status lights, the status lights are also synchronized, saying that we are actively participating in this log. So I'm going to abort this. And we should see that the status light should change to a more slow blink. Next part is to make a triggered acquisition and then disconnect the node. And to do that, I'm going to need help from Linus in a minute. But first, let's go into the trigger. So this is the trigger definition where the system know of. So I'm going to go into this disturbance trigger, and we see that the disturbance trigger on station 0, it detects if a frequency is out of range, if it's outside 1.9 to 2.1 hertz, or if we have our AC RMS value that's outside 7 to say 7.1. If any of these occasion occurs on station 0, we will start logging data, or if we detect a digital input on station 1. So we actually combine the station 0 and station 1 together. I'm just going to save this, and I'm going to close everything, and let's activate this trigger. So you can have a number of triggers that are just sitting and idling and waiting to be activated. Linus, if you could just change the frequency to 3 Hertz, please. And we should see that the frequency jumps up here. Here we go. Yes. We see that we've got the frequency step to 3 Hertz. We see that both systems start to logging, even if the frequency is just detected on station 0. Now I'm going to simulate that we have a network loss, and I'm going to do that by disconnecting the node from the system main switch. So let me take disable on this one. So what I'm expecting now is station 1 to turn yellow, indicating that station 1 is not connected. Here we go. The user interface just knows that there is one active node logging data. Station 0 still logs data, so everything seems to be okay. And let's see what happens if we take this back again. So here we go. So the network should be up and running again. And here we go. Station 1 comes back and it still logs data in the system. So Linus, can you please turn the frequency down to 2 Hertz again? Just otherwise I would have a retrigger, I guess. So here we go. And I'm going to abort this for the demonstration purposes. And I have a small application running in the background here, just to show you that the disturbance trigger, that first sample in the waveform detected on both station 0 and station 1 is the same timestamp. We also have the first log session that we did, where I had all channels first on station 0, and then I added station 1. There's a bit of difference between the start times of both of them, and that's because station 1 was not ready to have data at this point. And if I look at the triggered data in this case, I have disturbance triggered data. I have a number of segments on station 0. And I have a number, sorry, I have to refresh. On station 0, and I have a number of segments on station 1, and we can see that there's no segments missing on either of them. Both of them are complete. So if I would evaluate this data, I would have a complete set of data from this exactly the same time to the very end. So the next step, or the final step of the demonstration, is I'm going to first disconnect station 1 again. I'm doing the same thing. I'm disabling network connection to station 1. So I'm just waiting for this to turn yellow. And while we're not seeing this, I'm going to ask Linus to use a digital input to trigger the station 1. You can just tell me when you've done that, Linus. Okay, perfect. So station 1 should be triggered. We don't have any information of that. At the same time, I'm going to start the same trigger we had before manually. I'm going to start this all channel trigger. So what I expect now is that I should have 2 log files being generated on each of the nodes. Just turning station 1 back in the system again. And yes, so both of them are now participating in this logging data. So the disturbance trigger, that was triggered on an offline node in the digital input that Linus used. And station 0 triggered this demo all channels, which is a manual logging session. But both of them are logging at the same time. So I'm going to abort this. And I'm going to abort the all channels. And again, I'm going back to my little VI, my little application, and to see the disturbance trigger. We have the disturbance trigger on, let's see, where is it? Yeah, this is the demo channel. and this is the distribution channel. So this is both logging data on the same spot, and we can again go back and see in the triggered file that we're not missing any data. Let me just refresh again. So we have station 0 and station 1, and all the segments are still there in station 0 and station 1. So we demonstrated the ability of Lundby to have multiple calculations for a channel. We used the same channel and created frequency, RMS and AC RMS values. With the calculated channels are not generated at full speed. The data is collected at 20 kilohertz, but the output rate of all these calculated channels are just 10 samples per second in this case. And we also demonstrated that you can have trigger that span multiple nodes and combine both virtual channels and calculated channels. And I think that was the demonstration from me.
Okay. Stefan, any comment on your side?
No comment from me, no.
Okay.
I'm just going to comment on one thing Stefan said. Because Stefan, he mentioned that data is sampled at very high rate in the nodes and then reduced for sending the data up to the database. And that can be done, but we can also send the full speed data up to the database. It's a dual system. So we allow reducing the data before writing data to the TDMS files. But we can also write the full speed data and combine different kinds of sample rates into the same TDMS file.
Thank you, Jonas. The webinar will be recorded and will be hosted on ni.com. Together with our marketing team, we are organizing the hosting of the webinar, and then in case the people can see again and share the link to all other colleagues. So thank you everyone for attending. Thank you for presenting, Anna, Stefan, Jonas, and Linus, and have a good day, everyone. Bye-bye.
Bye.
Okay. Bye-bye.
Thank you. Bye.
Bye.